So this is my last video for Biochemistry 1 problem sets. In this video, we'll be going over 8, 9, and 10. So for number 8, it says that some bacteria can use nitrate as an electron acceptor instead of oxygen, reducing it to nitrite. And so the first part asks for a balanced equation for the oxidation of NADH by nitrate. So oxidation means that it's losing electrons. So you have the NADH, and it'll be oxidized to NAD+. Now it's kind of hard to see the loss of electrons, but you have to realize that the electrons are actually the two electrons holding the H to the NAD complex. So these two electrons are then being lost in the oxidation of NADH, and the nitrate is the one that will help out with this. So that's A. B says calculate the Gibbs free energy change under standard state conditions, okay, for the oxidation of NADH by nitrate. So we have to know the formula for Gibbs free energy change for standard state conditions. So this is the formula that we would use for that. Delta G is equal to negative NFE. Okay, so this is the formula that we had to use for this. And so we need to find this. This is the number of electrons transferred. This is going back to Gen Chem days. This is a constant, and the constant will be 96.5. And then this is just the standard reduction potential of the cell. So if you guys remember, this value needs to be positive. And if this value is positive, this value is positive, this value is n is positive. So these three are all positive, and then you have the negative, then it'll create a negative delta G, which is favorable. That means it's a spontaneous reaction. So we want this to be positive. Now we look at the standard reduction potentials chart, and it's in table 3.5. So if you refer to that, you'll see that the NAD plus NADH reduction potential is negative 0.32 volts. And then the nitrate reduction potential, nitrite is 0.421 volts. Okay, so the way that we calculate E is we do the acceptor couple minus the donor couple. So the acceptor minus the donor. So the acceptor here is 0.421, and then minus the donor, which is negative 0.32, and that gives positive 0.741 volts as this E value. So that is here. So we've got this now. We've got F, which is 96.5. And what would N be? Well, N is the number of electrons that are transferred. And as I referred to before, N, there are actually 2 electrons here that are being transferred. So this would be 2. So then if you just multiply them all together, you would get a delta G value of negative 143 kilojoules per mole, if you do the math right. So that's how you do 8B. 8C asks, so this is B. 8C asks, basically, the theoretical maximum number of ATP molecules that could be synthesized for each molecule of NADH oxidized by nitrate under standard state conditions. So with this reaction right here, we've generated this much energy. Remember, negative delta G means that we've created energy, we've produced energy. So we have this much energy in our bank. Now, we want to find how many ATPs we can produce with this much energy. Now 8C gives us some information that will allow to solve this. It tells us that in order to create ATP, one ATP basically, making one ATP, it takes 35.7 kilojoules per mole. So this is a pretty simple problem actually, that if we have this much energy and it takes this much energy to make one ATP, then how many ATPs can we make? Well, then you would just do 143 divided by 35.7, and you would get around 4.0 ATPs. That's the maximum theoretical number of ATPs that you can make if you were to oxidize NADH with nitrate. Okay, so that's C. D is pretty similar, and it says that the oxidation of NADH by O2, so this was by nitrate up here, but by O2, it is -219 kilojoules per mole. -219 kilojoules per mole. That's the delta G for the reaction if it were by O2. So now it's saying, now what is the theoretical number of ATP molecules that you can make? Again, it's a very simple calculation. You just do 219 divided by 35.7, and you would get around 6 or 6.1 ATP. So I'm just going to put 6. Now it says, comment on the energetic difference between oxygen and nitrate respiration. So with nitrate respiration, we made 4 ATPs. With oxygen respiration, we made 6 ATPs. So the nitrate respiration is around 2/3 of the efficiency of the oxygen respiration. So this is a lot more efficient than this one, and this is 2/3 of this. So I would just put something down about that. Now E says that the true number of ATP molecules for each NADH produced, for each NADH oxidized, is actually around 2.7. So it's not this actually. It's actually 2.7 in real life. I'm gonna use some text terms right here. In real life. So why is that? Well, one reason is because that in the real world we don't actually operate with 100% efficiency. When we had calculated these were theoretical maximum yields, but in real life there are going to be some conditions and I guess it's the environment in general that will prevent the real life from happening. So it's not as perfect. And two, in the calculation we assume standard state conditions, right? But our body does not operate in standard state conditions, so it doesn't apply to real cells. So those two reasons are the reasons why our yield is not as effective, or in real life how the yield is not as effective as the theoretical yield. So I'll actually email out number 9, the solution number 9, and I will just go over number 10 here. So for number 10, you're basically studying oxidative phosphorylation in bacteria, and find that for each succinate oxidized, you find that 6 protons are translocated. 6 protons are translocated. And so you can estimate that the bacteria makes 1.5 ATP for each 2 electrons that enter the electron transport chain. How many C subunits does the organism's ATP synthase, does the organism's ATP synthase have? So essentially, you know that in the problem it says that you have 1.5 ATP for made per each 2 electrons that enter the electron transport chain from succinate. Now, the way these two correlate is that succinate actually goes to a specific complex that you guys will learn about in the electron transport chain, and each FADH2 will essentially give 2 electrons, and so basically 2 electrons will be equivalent to 6 protons. So essentially I can go on the leap and say that 1.5 ATPs will be made per 6 protons. I know that wasn't too clear, so let me try repeating myself, that you have 1.5 ATP that are synthesized per 2 electrons that go from the succinate. The succinate actually goes to a specific complex, and where the FADH2s that the succinate deals with drop off their electrons and are oxidized, and so that's where these 2 electrons come from. And the complex at which they are oxidized, for each 2 electrons, they pump 6 protons. So if I say that there are 1.5 ATPs produced per 2 electrons, I can synonymously say that I have 1.5 ATP synthesized per 6 protons. Okay, so that's where we are right now. Now we want to see, we basically want to find out the number of C units. How many C subunits? So what is a C subunit? So there are a couple of rules that I would follow when going through this. The first rule is that essentially one rotation of the synthase, of the ATP synthase, will yield 3 ATP. Another rule is that the number of protons needed for one rotation is equivalent to the number of C subunits. And in this case, 1.5 ATP, 6 protons can create that. So with this much information, we can figure out the problem. Okay, so we know that 6 protons creates 1.5 ATP. And we know that one rotation makes 3 ATP. Hence, 6 protons are required to make 3 ATP, and so 6 protons will lead to, 6 protons make 1.5 ATP, and a full rotation creates 3 ATP. So we know we've made half of a full rotation. So the synthesis of 3 ATP would require 12 protons to move through the synthase. So if I need 12 protons for one rotation, then I have 12 C subunits. So to repeat myself, I know that 6 protons make 1.5 ATP. Okay, I know that one rotation of the ATP synthase was I would lead to the formation of 3 ATP, and I know that in order to make 3 ATP, I need 12 protons. So I need 12 protons for the rotation of the ATP synthase, and if I need 12 protons for the ATP synthase, then I have 12 C subunits to drive one rotation. So that's how I figured out A. For B, the oxidation of NADH in E. coli is accompanied by the translocation of 10 protons across the cytoplasmic membrane. So in B, I have 10 protons that are translocated, and I have 15 C subunits. So how many ADP molecules are phosphorylated into ATP for each 2 electrons originating from NADH? Okay, so the logic behind this one is one full rotation requires 15 hydrogens, 15 protons, because the number of protons needed for run one rotation is equal to the number of C subunits. If I have 15 C subunits, I need 15 protons for one full rotation. And one full rotation, as we know, will make 3 ATP. Hence, I have 10 protons, which is 2/3 of one full rotation. So if I have one rotation making 3 ATP, 2/3 of a rotation will make 2 ATP. So I will make 2 ATP. All right, so that actually concludes biochemistry problem sets, and it's been fun. See you guys, and good luck on your careers.